Hi, my name is Anna Blumenthal, and this is my ME3210 Design and Manufacturing Project 3, which is a design and manufacturing topic overview. So the objective of this project is to pick 5 design and manufacturing topics to delve deeper into, and these are topics that we've discussed in class and come from our lecture slides and the textbook. So in this presentation, I will be discussing what these techniques and processes are, advantages and limitations for using them, and why I'm interested in learning more about them. So the topics I will be discussing are continuous casting, thread rolling, deep drawing, design for X, and product lifecycle management. The first process I will be talking about is continuous casting. So as you can see from the image on the left from the textbook, this process involves first using a solid starter, which is added to the bottom of the mold. And so this helps support the metal while it's cooling so it doesn't deform excessively. So once that happens, molten metal is poured onto the starter bar where it then starts to solidify. It solidifies quite quickly, as you can see in this image. It is poured on the left side and it is cooled significantly on the right side. So it's a quick cooling process. And so when it cools, it solidifies, and then at the same rate that the metal is poured, the bar is withdrawn by pinch roll, so the bar just keeps rolling along. And once cooled, the metal is cut by shearing or torch cutting. So then the bar is cut into smaller pieces based on the products that companies need. So continuous casting is a manufacturing method used to cast non-ferrous, which is any metal without iron or iron alloy, metal strips. So materials that are used for continuous casting include steel and aluminum. The products manufactured using continuous casting include billets, blooms, rounds, and slabs, and these are used for infrastructure in buildings and in other components, but they have a lot of strength. And so some advantages for using continuous casting as a manufacturing method is that the manufacturing process is very efficient. As you can see in this image, you can produce a lot of material in a very short amount of time. And it is very cost effective. So the continuous process of having the bar created start to finish by pouring a mold and sending it down along rollers in the manufacturing process is very efficient, and it doesn't involve a lot of different machinery or a lot of relocation of the material. It's a straightforward process. And so a limitation for continuous casting includes a high setup cost, which its cost effectivity in the manufacturing process, I think, outweighs the cost going into the setup. Why I like it is that this was a manufacturing process that we learned about in class that I definitely wanted to learn more about because I wanted to learn more about different infrastructural just materials and also like the manufacturing processes that go behind them in different industries. The second topic I will be discussing is thread rolling. So thread rolling is a process where threads are created on round parts by moving them through rotating or reciprocating dies. So this is a cold forming process, which means that the round metallic piece isn't heated in any sort of way for these threads to be created. Some materials that are used for thread rolling include steel, stainless steel, aluminum, brass, and titanium. A couple advantages for using thread rolling is that it has high quality and high strength. As you can see in this top image, when a material is machine threaded, the fibers of the material are not changed in any way, but when they're roll threaded, when the thread is rolled, the pores are relocated based on the manufacturing process, and so it creates a stronger finish for the product being created. It has high strength, it is cost effective, which is beneficial, and has high fatigue resistance because of the fibers in the material not or adjusting for the shape of the material. A couple limitations to thread rolling are that brittle materials may fail due to thread rolling because it deforms the initial material, and so this isn't a viable manufacturing process for all materials. Why I like thread rolling is that in the both previous design and manufacturing projects, I proposed solutions that involved incorporating a nut or a bolt with threads on it to improve a product. So this is a manufacturing method that I've done a little bit of research on, and I keep being drawn to and thinking of design idea solutions, and so I wanted to learn more. So the flat die thread rolling process, also known as cylindrical die thread rolling, it is used to create external threads on bolts, studs, and screws, and has a high volume production. And the process involves two dies with engraved threads. One remains stationary and one rotates, and a cylindrical workpiece is then inserted between the two dies. And so the threads are then formed when the rotating die presses against the workpiece. The next manufacturing process I will be talking about is deep drawing. Deep drawing is a process where a flat sheet is formed into a three-dimensional part when a punch pushes a blank into a die cavity. This is used to make pots, pans, kitchen sinks, containers, and beverage cans. And so common materials used in deep drawing include aluminum alloys, copper, brass, low-carbon sheet metal, and stainless steel. A couple advantages for using deep drawing include that the shapes have no seams, which reduces the weak points in a product, which increases the odds that the product will not fail. Low maintenance during manufacturing process, so it's a straightforward manufacturing process. It has efficient cycle time, and the component is very uniform, so you can create a lot of nearly identical components using deep drawing. A couple limitations for deep drawing is that it's more complicated than metal stamping, which, because in order to finish the process, ironing, beating, or flanging may be involved. And why I like deep drawing is that hydraulic presses are used to power deep drawing, and I like processes that are hydraulic, and that's something I've done a lot of research in a work experience. The process for deep drawing includes having a circular blank being placed over a die opening, and it's held in place with a blank holder. A punch then forces the blank into the die cavity, and a couple deep drawing factors to consider when doing deep drawing is the sheet metal's mechanical properties, the sheet thickness, the punch and die clearance, and the punch speed. The next process I will be discussing is design for X. And design for X is just various factors that one considers when designing and manufacturing a product, and it can be designed for maintenance, it can be designed for accessibility, designed for human factors, designed for ergonomics. The one I'm focusing on is design for maintainability. So this is a design consideration that emphasizes the reduction of cost and improving accessibility for a product to be maintained. Ways to design for maintainability can be to improve access for a maintenance engineer to inspect or remove components, limiting the number of fasteners in a design, making features with lower life expectancies more accessible to somebody to look at them, and using industry standard components in a design. So these are all ways to make the maintenance process for a product simpler and more accessible for those who are maintaining the product. Couple advantages is that this decreases the cost for maintenance. It can reduce downtime. It can lead to safer maintenance procedures and easier troubleshooting processes, and it's time efficient. A couple limitations include it increases time and cost in design and manufacturing stages. And I'm interested in this because in previous work experiences, I talked with people in tech services for rides and show figures at a theme park, and they said that a design factor that isn't considered as often as that needs to be is designing for maintainability, because a ride can't go if it can't be maintained and inspected on a daily basis. So that's why I'm interested in it. The next process I will be talking about is the product lifecycle management. So product lifecycle management, or PLCM, is our strategies manufacturers implement as a product is developed through its cycle, and time emphasis on product development in the design phase is prioritized, so most of the thought and time spent on creating a product happens earlier so that it can lead to greater success in the later design phases. The product life cycle is all stages a product goes through in its life. So it starts with design, development, production, distribution, use, and then disposal and recycling. Why I like product life cycle management is that I have previous experience in project management. I like working with a project to develop a project from start to finish. So I like also identifying needs in consumers and using that to develop products. So a couple advantages for product lifecycle management is that it improves product quality and it can help drive future product design, it reduces risks, and improves cost management. A couple limitations include a waste of money and time if the consumer needs aren't correctly identified, and product replacement needs to be identified early. So on this graph, it shows the time into the design process, and the knowledge for design behavior shows that a lot of the time is spent at the beginning of a product development phase. Alright, a disclosure is that this video is created for educational purposes only, and that the information I presented reflects the knowledge I have learned so far in this class at this point in the semester. Here is my work cited, includes the textbook and lots of research. Thank you for your time.